All right, so we're going to look at this question. It's August 2021, number 8. And it says to go ahead and prove that cosine of the square root of z equals z has infinitely many solutions. Okay, so this is kind of a big theorem of complex analysis question. And our main tool that we're going to use, our main theorem is, I think it's the big Picard Theorem. And what this says is that if f is analytic aside from an essential singularity at z0, then f attains, let me rewrite this, then in any punctured neighborhood of z0, f attains every value in the complex plane with at most one exception. All right, so let's see how we can use this theorem. So first things first, all right, I want to go ahead and show that cosine square root of z minus z is entire. All right, I'm going to show that this is entire. So z is definitely entire, right? That's no problem there. We also know another thing. We know cosine of z is entire. But, all right, and this is an important but, root z is not entire. So our challenge here is to show that the composition cosine of square root of z is entire, and then this whole function will be. So sort of the easiest way to see this, at least algebraically, is to just write down the Taylor series for cosine square root of z. Right, so cosine of z is just going to be the sum n equals 0 to infinity of -1 to the n z to the 2n over 2n factorial. So then if we replace z by root z in this series, we get a nice Taylor series expression for cosine of root z, n equals 0 to infinity, -1 to the n, and then this z to the 2n just becomes z to the n over 2n factorial. And what do we have here? Well, I mean, this is definitely a convergent Taylor series. Moreover, there are no square root of z's in sight. Right. So we've kind of basically gotten rid of our problem. The evenness, or the fact that all of the terms of cosine of z are even powers of z, kind of cancels out the issue with the root z. Just to see this a little more and provide some intuition again for why cosine square root of z is entire, let's think about why square root of z is not entire, right? And recall, right, that square root of z usually requires a branch cut. And it requires a branch cut in general, right? Because it's multi-valued. All a branch cut does is it limits our domain of consideration so that the function is no longer multi-valued. So to write this out explicitly, square root of z generally has two solutions, plus or minus w. But, right, cosine is an even function. So if we plug in square root of z, we have cosine of square root of z is cosine of w is cosine of negative w, right? Where this is true because cosine is even. Okay. So in other words, the evenness of cosine fixes our multi-valuedness, all right? Even though square root of z is multi-valued, when you compose it with the cosine function, the resulting function is no longer multi-valued, it no longer needs this branch cut, and it's most certainly entire. Okay. So we're concluding here that cosine square root of z minus z is an entire function. Okay. So let's recall our big theorem, right? If f is analytic, aside from an essential singularity at z0, then in any punctured neighborhood of z0, f attains every value in the complex plane with at most one exception. So this theorem has to do with first analytic functions, but then also functions that have essential singularities, all right? So if you recall, all entire functions can be classified by their type of singularity at infinity, all right? So the types of entire functions we've got three types. Either no singularity at infinity, these are our constants. We could have a pole at infinity. These are our polynomials. Or finally, we could have an essential singularity at infinity. These are generally referred to as the transcendental entire functions. So let's look at this. That's not a constant. It's not a polynomial. It is, in fact, a transcendental entire function. So cosine square root of z minus z has an essential singularity at infinity. Okay, thus, by our big theorem, by big Picard, cosine of square root of z minus z attains every complex value infinitely often or infinitely many times with at most one exception. Okay, so what do we have to do to finish this proof off? Well, right, our original goal was to show that cosine square root of z equals z infinitely many times. Or equivalently, cosine square root of z minus z equals 0 infinitely many times. So the big Picard theorem is telling us that if this function here if this attains 0 once, if we can just find a single z value, then it's actually going to attain it an infinite number of times. Okay. So all we have left to do is show that this function, cosine square root of z minus z, attains 0 somewhere. So luckily, this function actually attains 0 on the real line, and we can show this as follows. So let's consider just the real valued version of this function. So cosine square root of x minus x, where x is real valued. So clearly this is continuous. All right. Then I'll just do a couple quick evaluations. At x equals 0, cosine of 0 minus 0 is 1. At x equals, let's say, what's another nice one we could do? Let's say x equals 4 pi. We have cosine of, So what I'm trying to do here is use the intermediate value theorem. I don't think this should be too hard. Yeah, let's just do this. X equals 4 pi squared. Then cosine of square root 4 pi squared minus 4 pi squared. That's equal to cosine of 2 pi minus 4 pi squared, which is 1 minus 4 pi squared, which is certainly less than 0. Okay, so what have we done here? Well, we've shown that in this interval from 0 to 4 pi squared along the real line, the function cosine square root of x minus x must have a 0. So we'll write that here. Cosine root x minus x has a 0 in 0 to 4 pi squared by the intermediate value theorem. Okay, and then finally, kind of tracing our logic back up, we know that since cosine square root of z attains 0 once, it has to attain it infinitely many times. So overall then, cosine square root of z equals z infinitely many times. All right, and that'll do it.